Assalamualaikum and hi everyone. Today I will be explaining two problems of structural analysis which are related to force method. The first one is force method on beam and the second one is force method on a frame. Okay, for question 1, this is the problem, this is the beam. As you can see, the question says use force method to determine reactions at the supports for the beam shown in figure below, then draw the shear and bending moment diagrams. Assume support B is roller, EI constant. So we can see B is roller, this is fixed. There are several steps in solving this kind of problem. The first step is principle of superposition. First, we need to inspect the beam. By inspecting, this beam is statically indeterminate to the first degree because it has one extra force. For this problem, I choose force at pin B. This is the force here as the redundant force. And then we draw the principle of superposition. First one is actual beam, where it is the same as the question. And this is the primary structure where we remove the redundant. And as you can see, after we remove the redundant, there is a deflection here, which is delta B. And this is when we apply the redundant back, we get one more deflection, which is delta prime BB. And after doing this, we need to do the Whitchell work. Why do we do Whitchell work? To find the flexibility coefficient. What is this? This is FBB is deflection due to one unit load. After we obtain this value, we can know the deflection at here by multiplying BY with this flexibility coefficient. Okay, the next step is compatibility equations. This is the compatibility equation for our beam just now. It is 0 equals to negative delta B plus delta prime BB. Delta B is negative because positive displacement is assumed upwards. That means, as you can see, this deflection is downward, so it's assumed negative. This is upward, so it's positive. Okay, and we know delta prime BB is equals to FBB times BY. So this is our actual compatibility equation. It's negative delta B plus FBB times BY. To find delta B, we know this formula you can get from the table. Then we just plug in the values. We can get delta B, and we can get, this is our delta B, and we can get our flexibility coefficient, which is this one. Then we plug in the value into this compatibility equation to get our BY. This is our BY. This is our BY value now. And the last step is equation of equilibrium, and this is to find the other reactions, because now, as you know, we already got our redundant force value, so we can find the reaction of our other support. Okay, then just do a normal equation of equilibrium. First we do Fy. By doing Fy, we get the value of Ay, which is this value. Then we do Fx. Ax is 0 because there is no horizontal force. Then we do the moment. We get our moment. This is the value of our moment. So the answer for reactions at support, Ay is 5 WL over 8, By is 3 WL over 8, moment at A is WL square over 8, Ax is 0. And this is our shear force diagram. This is how it looks. And this is our bending moment diagram. Yeah, that's all for question 1. Okay, for question 2, the question is use force method to determine reactions at the supports for the frame shown in figure below. Assume A and C are pins and the joint at B is fixed connected. EI is constant. Okay, so the question asks us to assume A and C as pin. So as usual, we have 3 steps, and the first is principle of superposition. First, before we do anything, we need to inspect the frame. So by inspection, the frame is statically indeterminate to the first degree because we have 4 reactions. So it's indeterminate to the first degree. And for this problem, I choose horizontal force at pin C, which is Cx, as the redundant force. So I choose this force as the redundant force, Cx. Okay, next step is draw the principle of superposition. This is the actual beam, same as the question. And as we can see, the actual deflection of the beam is like this and like this. This is the actual deflection. This is when we remove the redundant. This is primary structure where we remove the redundant CX, and we can see the deflection of this beam is changed to this, and this is our delta C here. And this is when the redundant CX is applied, we got this deflection, which is delta prime CC. And the next step is we do visual work to find our coefficient here, so that we can know the value of this delta prime CC, which is CX times FCC. FCC is the deflection due to 1 unit load. The next step is compatibility equation. This is our compatibility equation, which is negative delta C plus delta prime CC. And as we know, delta prime CC is equals to CX times FCC. Okay, for this question, to find the delta C, the formula is different from the first question. For this question, we need to find the internal moment. The capital M is the internal moment at the primary structure, and the small m is the internal moment at the virtual work. So our first step is we need to find the internal moment. Okay, so we must draw back the primary structure. And to find the internal moment, before we find the internal moment, we must know the reactions first. The reaction at the primary structure. So I did this calculation and I got AX 90 kilonewton, CY is 202.5 kilonewton, and AY is 157.5 kilonewton. When I get after getting the reactions at this all these reactions, now I can find my M1 and M2. M1 is here. This is our M1. We get negative 30 x1 square plus 157.5 x1. And our M2 is here. For M1, we assume it positive because it's anti-clockwise. For M2, I assume it negative because it's clockwise. So our M2, we can see negative here. So our M2 is negative 15x square. That's our value for capital M1 and capital M2, which is the internal moment at primary structure. Next, for virtual work, we do the same thing as we do here. First, we find the reactions. As you know, if here it's 1, 1, 1, then here is 1. Here it will be 1. Then we do the calculations. We will get 0.5 and 0.5. And our small m1 is 0.5x1, which is here. It's positive. Our m2 is here. Our m2 is x2. Okay, that's for then after that, now we can find the value of delta C by putting the values of our m in this formula, both of this formula. Okay, so the first one is delta C. We just plug in all the values, and we will get our delta C is equals to 506.25 over EI. And next is our FCC. Do the same thing. Just plug in the value into the formula, and we will get 27 over EI. Okay, now we can use both of these values to find our CX, where we can put these values in our compatibility equations, and we get our CX. This is our CX value, which is negative 18.75 kilonewton. Now our last step is equation of equilibrium. Now, as we know, just now we cannot find the support reactions because we have one redundant, but now we know the value of the redundant, which is 18.75 kilonewton. So now we can do our equation of equilibrium and get the values. First, we do for Fx. The summation of Fx equals to 0. Ax equals to 108.75 kilonewton. Then we do moment at A. By doing moment at A, we can get the value of Cy, which is 211.88 kilonewton. Then we do Fy. By doing Fy, we can get the value of Ay, which is 148.12 kilonewton. So now we have already answered the question, which is the question asks us to find the reactions, the support reaction, value of the support reaction. So we get all the values already. Ax is 108.75, Cy is 211.88, Ay is 148.12, and this is our Cx value.